All right, advanced placement chemistry. This is day 85, equilibrium. We're going to work some problems from the book today. This is due on Thursday. So write the expression for Kc, the equilibrium constant for concentration, for the following reactions. In each case, indicate whether the reaction is homogeneous or heterogeneous. Okay, so let's go ahead and do that. All right, so A. So the equation. All right, so it's products over reactants, so Kc. Coefficients of both are 1, so the exponents are 1. And that's to the third power because the coefficient here is 3. All right, the type of reaction, it's gas, gas, gas. It's the same state, so that's what's meant by a homogeneous equilibrium. Okay, and so what we have here is all right, and all four are in the gaseous state, so that's also homogeneous. Again, let's just be sure we're clear on everything. Products go on top, that's this. Coefficient 1 and 4, so exponent is 1 and 4. Reactants go on the bottom, these two. Coefficients of 1 and 2, so exponents of 1 and 2. All right. All right, so now we are going to write this is going to be Kc. And products go on top, which would be CO. CO. Exponent is 4. Ni is in the solid state. You do not include solids or pure liquids in a law of mass action, so we don't put that in, we just ignore it. And on the bottom we do have a gas, so it's Ni. Again, the subscripts have nothing to do with the exponents. They just go where they go. And this has a coefficient of 1, so that's a 1. So that we have that. Now, since we have gaseous and solid together in the same equation, that's going to be heterogeneous. Okay, and that was, by the way, problem 1513. Okay, next up is 1516. So which of the following reactions lies to the right, favoring the formation of products, and which lies to the left, favoring the formation of reactants? All right, so we can just look at the book for this one. So this one is a huge number, 5 times 10 to the 12th. Remember that the K, any kind of a K variable, any kind of an equilibrium constant is products over reactants. That means to have a number this big, you must have far, far more products than reactants because it's a very, very large number. That means this first one, A, is favoring the the products. You look at the one down here, it's a very, very small number, 10 to the minus 18th. That means that the products on top are very, very small compared to the concentration of reactants on the bottom. So almost none of this reaction has taken place. This would be an example. This would be could be some kind of an insoluble substance that just doesn't dissolve. So a very, very tiny fraction of it actually does. Most of it does not. So the bottom B, the bottom reaction B would favor the reactants. The top one, A, would favor the product. So let's just write that out. Part A, is 5 times 10 to the 12th is very large. The product in the numerator of the equation, the products in the numerator of the equation are much greater than the reactants in the denominator. Therefore, products are favored. For B, Kc is 5.8 times 10 to the negative 18th, means that the denominator reactants is much larger than the numerator products. Therefore, the reactants are favored. All right, and we'll move on now to 15.23. Okay, so 1523, the following equilibria were attained at 823 K. Again, the only significance is you have to specify a temperature, and as long as that temperature doesn't change, you can work these problems. So there's the two reactions. It gives you an equilibrium constant of 67 for the first reaction, and an equilibrium constant of 490 for the second reaction. Based on these equilibria, calculate the equilibrium constant for H2CO2, H2 plus CO2, producing CO plus H2O at the same temperature. Okay, so the point of this question is we're given two equations up here. We have to reproduce this equation down here using those. So we have to manipulate these in much the same way as Hess's law, but then we also have to change these accordingly. And remember, the rules are not the same as they are for enthalpies in Hess's law, but we were given the rules in the PowerPoint presentation. Okay, so what do we have to do? Again, look for things that appear only once in these equations. And H2 appears, there's an arrow, there's an arrow. So H2 appears on the left, and it's on the left of the final equation. So we don't want to reverse this equation. And since the coefficients are the same, we don't want to multiply this through by any kind of a factor. So we're going to leave equation 1 as it is. Okay, what else do we see? Also, water appears on the right-hand side of the arrow and on the right-hand side. So equation 1 looks good. Now, let's see, CO2. CO2 appears on the right-hand side of equation 2, but it appears on the left-hand side of the overall equation. They both have the same coefficient of 1, so it leads us to believe what we need to do is just switch equation 2 around, reverse it. Okay, so we're going to go ahead and do this. So this is 2A, and we're going to reverse that. So we're going to end up with CO2 here. Okay, so then the question is, we've reversed the equation 2, we've turned it around. Let me just check my work here. And it all looks good. So what does that do to this? Well, in Hess's law, you might remember it changed the sign. Here it doesn't change the sign, it creates the reciprocal. So the reciprocal of 490 is going to be what we're going to put here. So that new Kc is going to equal, okay, so for right now, we'll just call it 1 over 490. So that means Kc for our overall equation is going to be, we can go ahead and put a line through 2 because we've used it, it's done. So what do you do then when you, we now added these two equations after we did the reversal to get this. So what do you do with your K's when you add the two equations? You multiply them. So that's going to be Kc and we'll just call it of equation 1, and that's going to be multiplied by Kc of equation 2a, the new 2 equation there, and that's going to equal our Kc of the overall reaction. Okay, so that's simply going to be 67 times 1 over 490. And that is going to equal, and that's going to give us Kc of the overall reaction equals 0.14. And that's the answer. Okay, now we're moving on to 15.24, very similar to the last problem. So we have an overall reaction here. We want to figure out what the equilibrium constant is from these two elementary reactions. So again, we look at how we have to arrange these to create this equation up here. So if we look at equation 1, we see NOBR, 2 NOBR here, and we see it in the final equation in the overall. So we know we don't want to change, it's on the right side of both. So we don't want to change equation 1 at all. It has the in the right location and with the right coefficient. All right, the overall has N2 and O2 on the left side of the arrow, and in equation 2 they're on the right side of the arrow. So we know we need to reverse that equation. So we're going to go ahead and do that right here. Call that 2a. And so that's going to give us over here is N2. And over on this side it's going to give us 2NO. Okay, so we're done with 2, so put a line through it. Now what you have to do is take the reciprocal of this. So I'm just going to call that for right now 1 over 2.1 times 10 to the 30th. That's a really small number. All right, and so now what cancels out? Well, the 2NO here and the 2NO here cancel out. So what that leaves us with on the left side of the arrow is Br2, O2, and N2, and those are up here in our final equation. And then the only thing left on the right side is the 2 NOBR, which is in the final. So we've taken care of it. So our Kc for the overall is going to equal 2 times 1 over 2.1 times 10 to the 30th power. Okay, so the way we run this on the calculator is it's 2 times 1 times over 2.1 times 10 to the 30th. So it's basically 2 divided by 2.1 times 10 to the 30th. So I'm going to write 2, and then I'm going to divide that by, and I'm going to put this in parentheses, 2.1 times 10 caret 30. Be sure you can see this like that, and then I'm going to close the parenthesis and I'm going to hit equal, and it gives me 9.5, that's as far as we need to go in that, times 10 to the minus 31. So the way the calculator shows, it doesn't show the times 10, it just shows the exponent there. So it's 9.5 times 10 to the negative 31st power, and that's the answer. Okay, so 1526, consider the equilibrium, and there's the expression. Write the equilibrium constant expression for this reaction in terms of partial pressures. So pressures are treated exactly the same as concentrations, it's just you use the letter P with the subscript of whatever the compound or element is. Otherwise, you write the equilibrium constant expressions the same way. B, why doesn't the concentration of N2O appear in the equilibrium constant expression? Okay, so let's go ahead and write that equation out and look at it. Okay, so let's go ahead and write that equation. All right, so when we write this, we're going to write it, but you exclude liquids and pure solids. Well, we have pure liquids and solids, I should say. Well, it looks like you got solids in two different locations, so you're not going to include those. So what's this going to look like? It's going to look like this. Okay, and you use the subscript P because it's pressure equals, well, there's on the product side, there's only a solid, so there's nothing there, so you just put a 1. And on the reactant side, you only have one thing you're going to include. It's this with the gas, not the solid. So it's going to be P of SO2. And that's it. That's how you would write it. So you can write the part B. This is part A. You can write neither Okay, so neither N2O nor Na2SO3 will appear in the law of mass action, or they call it the equilibrium constant expression, because both are solids. Okay, so that takes care of that problem. Okay, so let's go ahead and read this. So a mixture of 0.1 mole of NO, 0.05 moles of H2, and 0.1 mole of H2O is placed in a 1 liter vessel at 300 Kelvin. The following equilibrium is established, and there it is right there. And then at equilibrium, the concentration of NO is 0.062 molar. So calculate the equilibrium concentrations of H2, N2, and H2O. So a couple points. So they want the equilibrium concentrations. What they gave you up here are initial concentrations. We're going to make an ice table here, and we have initial concentrations, and then we have one final or equilibrium concentration right there. The other thing to notice here is that the H2O is in gaseous form. It's not in liquid form. We said if it's a liquid or a solid, you don't include it in the law of mass action. But here the water, H2O, is in gaseous form, so you do include it in the law of mass action. Okay, so let's go ahead and set up an ice table. And we have we just count. We have 1, 2, 3, 4 total products and reactants together. And we need a column for the words initial, change, equilibrium. So I'm going to just write off here. And we need 4 different rows, and I should say 5 columns. So I'm going to make 4 rows here. This doesn't have to be beautiful. It's nice to use a ruler, a straight edge, but just do what you can here. So that top row is the reaction. The second row is initial. The third row is change. And the fourth row is equilibrium. Okay, and I have 4 different reactants, so I'm just going to go ahead and kind of try to make these roughly even. Okay, there's the ice table. All right, so we can go ahead and just write the words here. Reaction. Initial, meaning beginning. Change. And equilibrium. Okay, and then we'll go ahead and write our reactants and products. And we have 2NO, again, you don't usually write the arrow, but it's nice to distinguish products from reactants, so I like to do it. Okay. Okay, so it gives us initial concentrations of 0.1 mole NO. We'll put that in the initial row. And then it's 0.05 moles of H2. And I'm going to maybe omit some of these trailing zeros here. And then finally it's 0.1 moles of H2O. Like that. The other thing that they give us is the equilibrium concentration of NO, and that's going to be 0.062. So it's kind of like a little puzzle. You just figure out what you can fill in here. So it looks pretty clearly we can fill in this. And we know the initial, and we know the final, and we know it's going to be reduced because these two are reactants. So we just do a little subtraction and we figure out what the change is. Okay, so this is going to be 0.038, and it's a negative sign because it's being reduced. It's a reactant. Okay, so now that helps us fill in some of the others. If there's 2 moles of NO and 2 moles of H2, that's a 1-to-1 relationship. However many moles of this there is changing, there's going to be the same amount of this has to be changing for the reaction. So if you got to use up 2 moles of NO to make this reaction work and 2 moles of H2 to make this reaction work, what it's really saying is you need to use the same number of moles of NO as you do of H2. So since we changed by negative 0.038, this is also going to be negative 0.038. All right. And since this is also a 2, so all of these are 2s, and this is a product, it's going to be increasing by that same amount. So this is going to be positive 0.038. And of course, the only one that doesn't have a 2 is this one. That's 1. So this is going to be half as much as either any of these. Let's focus on this one. This is going to be half as much as this because it's 2-to-1. So that means this is going to be 0.19. And since it didn't give us an initial concentration of N2, you assume it's 0. So you add this and you get 0.019 here. You add this and you get 0.138 there. And then you have to do a subtraction over here. And that's going to give us, pretty sure it's going to be 1,2. Okay. Good. So we filled in our ice table, and the part about it is now keep in mind. Yeah. So that's it. So the question was, what are the equilibrium concentrations of N2, H2 of N2? Yeah, H2, N2, and H2O. So there's H2, there's N2, and there's H2O right there. Those are the equilibrium concentration. Okay, so this was part A. Part B is asking you for Kc. So Kc is going to be, let's just write the general law of mass action for this. It's the products over the reactants. So it's, and these are concentrations, they're molar concentrations. So it's N2 is one of our products. It has no coefficient, so the exponent is 1. It has a coefficient of 1, so the exponent is 1. H2O has a coefficient of 2, so the exponent is 2. Now we go down to the bottom for the reactants. You have NO down there. A coefficient of 2, exponent of 2. And H2. And coefficient of 2, exponent of 2. Okay, so now plug in some numbers. Got to use parentheses on the calculator. N2 is 0.019, right there, equilibrium of N2. We're not interested in anything above now. For this, we're interested purely on the equilibrium line. H2O is 0.138. and coefficient is the 2, or we don't even have to go up there anymore. Right there's 2 is squared. Now we come down on the bottom. NO squared, so there's NO. And that's squared. And then you have H2. And that's squared. And when you go ahead and run all those numbers, check my numbers real quickly here. Okay, and you're going to get approximately 7 times 10 to the second, or 700. Again, I rounded differently than the book, but that's the answer they get, and my answer is about the same. And I get 654, but they're, of course, using significant figures, so that's as close as they can get, is 700 to 654. Anyway, same answer, and it's all good there.